All right, let's dive into GCSE AQA Physics. Today, we're tackling energy.
We'll be looking at how it's stored, how it changes forms, and why it's so important.
No lab coats needed. We'll break down those formulas and look at real-world examples.
We'll even touch on renewable and non-renewable energy sources.
Sounds great. So where do we start?
First, let's define a system in physics. It's
Okay.
like a collection of objects we're looking at.
Like a car driving. Would that be a system?
Exactly. It's important to know the boundaries of that system.
Got it. So how does energy come into play?
Imagine you're playing pool. You hit the cue ball, transferring energy to it. Then that cue ball hits another ball, transferring some of its energy.
Oh, I see. So the energy is like bouncing around within the system.
Yes. And this brings us to kinetic energy, the energy of motion. That speedy cue ball, that's kinetic energy.
So the faster something moves, the more kinetic energy it has.
Right. But it also depends on the mass. A heavy truck at a certain speed has more kinetic energy than, say, a feather at the same speed.
Makes sense. I wouldn't want to get hit by that truck.
Exactly. And the formula for kinetic energy shows this. It's half the mass times the velocity squared.
So if I want to calculate the kinetic energy of like a roller coaster, I need its mass and speed.
Yep. And that's why roller coaster designers have to be very careful because of all that kinetic energy.
Now, what about potential energy? It's like energy that's just waiting,
Yes. Think of it as stored energy with the potential to do work.
like a stretched rubber band.
Perfect example. And you remember the formula for elastic potential energy, right?
Yeah, I think so. It's E equals 1/2 k squared.
Yes,
Right.
where K is the spring constant and E is the extension.
Right. And what about that roller coaster? But when it's at the top of the hill, that's potential energy too, right?
That's gravitational potential energy, the energy because of its position above the Earth.
So the higher it is, the more potential energy.
Exactly, and the formula includes height. E equals mgh.
With m for mass, g is gravitational field strength, and h is height. All right, I think I'm getting this potential energy thing. What's next?
Let's move on to thermal energy.
Ah, yes, thermal energy. I remember learning about specific heat capacity. Something about how much energy you need to raise the temperature.
Yes, and the formula for that is E equals AMC delta T, where C is the specific heat capacity. It tells us how much energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius.
So different materials have different specific heat capacities.
Absolutely. Water, for instance, has a high specific heat capacity. That's why it takes a while to boil water. It takes a lot of energy to raise its temperature.
So that's why a metal spoon heats up faster than the tea itself.
Exactly. Metal has a lower specific heat capacity.
Makes sense. So we've talked about kinetic, potential, and thermal energy. What else is there?
Well, let's talk about power. It's the rate at which energy is transferred, how quickly work gets done, you could say.
So a powerful engine can do the same work as a weaker one, just faster.
Precisely. Imagine two cranes lifting the same load to the same height. The more powerful crane will be faster because it has a higher rate of energy transfer. And the formula is P equals E over T.
P for power, E for energy transferred, and T for time.
You got it.
All right. So we've talked about energy transfers, but what about that key principle you mentioned earlier
Right.
about energy conservation?
Right. Energy can't be created or destroyed, only transformed. But here's where it gets interesting. Even though the total amount of energy stays the same, the amount we can actually use can decrease.
I see what you mean, like some energy gets lost along the way.
Yeah. It's like when you inflate a tire.
Okay.
Some of that energy you're putting in, it escapes as heat because of the friction.
Right, you can feel the pump getting warm.
Exactly. Some of that useful energy becomes unusable heat.
So is there any way to, like, reduce that loss?
Absolutely. Think about those squeaky bike wheels. A bit of oil can really cut down on the friction.
Yeah, so less energy is wasted as heat.
Exactly. And speaking of making things smoother, think about insulation in houses.
Okay.
Materials like fiberglass or double-glazed windows, they slow down how fast heat escapes.
Right, so it keeps the house warm without needing to use as much energy.
Exactly. It's all about minimizing energy transfers that we don't want. And that brings us to efficiency.
Right, efficiency. That's how much of the energy we put in actually gets used for what we want it to.
Exactly. It's the ratio of useful energy output to the total energy input, usually expressed as a percentage.
So like if a system converts 80% of the input energy into useful output, it's 80% efficient.
Exactly. The higher the efficiency, the less energy is wasted.
Makes sense. So we're always trying to make things more efficient.
Yes, whether it's a car or a house or anything else.
Right. So we've talked about energy transfers, but what about how easily heat travels through stuff? I'm thinking of thermal conductivity.
Great point. Thermal conductivity is how quickly heat energy moves through a material. Metals have high thermal conductivity.
Right, that's why a metal spoon heats up so fast.
Exactly. Heat travels through it really easily.
And things like wood or plastic are bad conductors, which makes them good insulators.
You got it. Low thermal conductivity slows down the rate of that heat transfer.
Like a log cabin, keeps the heat in.
Yes. And understanding thermal conductivity is really important when designing buildings.
Yes, it is. Choosing the right materials can make a big difference in how much energy the building needs.
Absolutely.
This is all really fascinating. So let's talk about energy resources, the stuff we use to power the world. We have renewable and non-renewable, right? What's the difference?
Good question. Non-renewable resources, like fossil fuels, they're finite. We're using them faster than they can be replaced.
Right, fossil fuels come from ancient plants and animals, and they're not very environmentally friendly.
No, burning them releases harmful stuff into the atmosphere.
So we need to find alternatives. That's where renewable energy comes in.
Exactly. Renewable sources are constantly being replenished naturally. Sunlight, wind, water, and the Earth's heat are all renewable sources.
But I've heard that, like, solar and wind aren't always reliable. What happens when the sun doesn't shine or the wind doesn't blow?
That's one of the challenges. Their availability depends on the weather. That's why we need to be able to store the energy they generate.
So we need better batteries and other storage solutions.
Exactly. There's a lot of research happening in that area. Think about it. Using the power of nature to create a clean energy future.
That's a great thought.
Yeah.
It's amazing how much our understanding of energy has changed the world from the Industrial Revolution to now.
You're absolutely right. And this brings us to a really important question that I want you to think about. With all this talk about energy and climate change, how can we balance our energy needs with protecting the planet?
Yeah, it's a tough question.
It is. There's no easy answer. But we have the knowledge and technology to make progress.
So it's not just about finding new energy sources.
Right. It's also about using the energy we have more wisely.
Okay, so like those energy-saving tips we talked about.
Exactly. Using efficient appliances, insulating our homes, even walking or biking instead of driving.
Those things can really make a difference.
Absolutely. They all add up. It's not just about individual actions either. Governments, industries, researchers, they're all working on cleaner technologies.
So there's hope for a cleaner, more sustainable energy future.
There is. As we learn more about energy, we're finding new ways to power the world without harming the planet.
Well, we've covered a lot in this deep dive. We've talked about how energy is stored, transferred, and conserved. And we looked at those formulas for kinetic, potential, and thermal energy.
We even talked about the challenges and opportunities of renewable energy. It's a really exciting field.
I hope you're leaving this deep dive feeling energized and ready to tackle those physics problems.
And remember, the concepts we've discussed are everywhere. From your phone to the sun, energy is at play. Keep exploring and keep asking questions.
That's a wrap on our deep dive into energy. Until next time, stay curious.